time. Okay, you can stop. You can stop.
All right. Okay. Good evening, everyone. It's nice to finally meet everyone again. So I hope everyone is having a great night so far. So just a brief overview of what we've talked about last week. We already know how it's like to initialize the PSO, how to set our parameters, and then we also talked about how we can create the plots. So for this one, and then up until this part. So all of them are about the plotting methods. And we also talked about the first part of the primary PSO, which is this part, the normalization. Because again, in normalization, we have to organize the data so that everyone is systematic, sorry, so that the data is systematic and that it is organized once we input the data into the PSO and k-means clustering. And then in the first part of PSO, we always have to remember that we have to follow these codes without iteration. Again, we don't have any iteration up until this part. All right. But from this part up until the last part, we just really have to copy the codes that we have presented all over in the first parts, and then we just added this iteration. And again, what's the importance of iteration? For us to find the best G-best fitness. And when we say G-best fitness, is the least error that the model could produce. Since in your study in the Turkey earthquake or in most studies, we really wanted to minimize the error. That's why our cluster validity is SSE. So you can take a look at the SSE. And again, SSE is similar to statistical formula. We always have to reduce and mitigate error. Okay. So right now we're going to talk about how we can run this model already. So this is your guide. I'm going to send it to Dokyogi as well. So later on, you can just fill it in. So let's say you wanted to test your parameters in your Turkey earthquake data or in any kinds of data, you can use this guide because I also use this. You can just fill in the necessary data. So again, for this part, we always have to start with initialization. So I'm going to remove all the values so that you'll also know how can we input all the values. All right. So right now we don't have any values at all. Next, we have to identify what is our M. Again, when we say M, it's the number of clusters and it's always fixed in the beginning. But in we have to follow the formula square root of data points. So in this part, you just have to add your data points. So in the Turkey earthquake, let me just check it again. How many participants do you have? So let me just count. You have 509. Okay. So you just have to input 509 here. And then this is your M, 23. Now you have to put 23 over here. Okay, 23. And then next, we have to find our n. N is the number of particles, any value from 10 to 50. So from 10 to 50, you have to find significant references. You should always find references for N, W, C1, and C2. So let's just say, for example, I found a reference that says 10, 20, and 30 are good N values or are good particles based on a specific study. Okay, you always have to find a specific study. For example, I found a study related to Dokyogi. For example, Yogi et al. 2023. Mhm. Okay, all right. So what you're going to do next is to fill in the rest of the model with 10, 20, and 30. 10, 20, and 30. Next, what about our W? As we mentioned in this part, W is any values from 0 to 1. So it's often decimal. I do not really recommend using 0 or 1. I would definitely recommend something that has decimal values. So again, you have to find a relevant study again. So let's just say we have already found another study. Let's say um my surname, Cahigas et al. 2023. And in this study, for example, I found that zero point 0.4 and zero point 0.7 are best inertia weights. Okay, so you're going to input zero point 0.4 over here, zero point 0.4 in all the n, zero point 0.4 again, and zero point 0.4. But you have another zero point 0.7. That's why you have to put zero point 0.7, zero point 0.7, and zero point 0.7. Why did I put three 0.7? Because we have 10, 20, and 30. Okay. So for every n, you should always pair it with another w. All right. So they should always be paired. Next, again, for C1 and C2, they should always be equal. We just also have to find another reference. For example, we have found this reference. If your C1 is 1, then your C2 should also be 2. So for example, we'll put 1 and 2 based on our references. So we can include 1 first. C1 is 1, C2 is 1. And you have to copy everything up until this part. Okay. So now that we have completed up until these parameters, we have to find the combination for C1 and C2 equivalent to 2 because we haven't looked at it just yet. That's why you have to input 2. Okay, then just copy it for the rest. And the idea behind this is to just copy your combination from this part, copy this part, and then move it to this part. Okay. And why did I decide to utilize all these parameters? It's actually up to you how many kinds of values you want to check. Let's say you wanted to check 10 and 20, and or let's say you just want to check 0 0.4, 0 0.7, and then 0 0.8. It's also fine. It's definitely up to you. You can also choose 1, 2, 3, 1, 2, 3 for this part. But the thing is, you just have to test at least 10 parameters. So do not forget this one. You always have to test at least 10 parameters. So let's say your combination is just until, for example, your combination is just until this one, you have to perform another parameter setting. Okay?
So
All
far, so
right.
good, guys.
Mhm.
Yeah, this is like experimental design, like factorial design, like general orthogonal
Mm.
design, like that. Yeah,
All right, right. They do have
yeah,
some similarities.
yeah. It's almost
I just
similarities. Yes.
remembered.
Yeah. Okay, okay. Let's continue. Yeah.
Okay, all right. So now that you have your own parameter values, again, based on the references, you can already input them into your code here in the MATLAB code. So you have to test them one by one. So let's say I'm going to test parameter 1. What's my n for parameter 1? I'm going to test this one. My n is 10. I'm going to input 10. My W is zero point 0.4. Let's input zero point 0.4. Your C1 is 1 based on this part, and your C2 is 1 as well based on the Excel file. And for the dimension of data, when we say dimension of data, these are the number of columns, or these are the number of your indicators from the SEM. So let's go back to your raw data. Let's take a look how many columns do we have. So again, we have deleted all your the intention to I'll just
Donate.
check this
Intention
one.
to donate and
Ayun,
intention
intention to
to
donate,
volunteer.
intention to volunteer. Okay. So
Yeah.
don't forget that we have to remove the indicators for this part and then this part. So you just have to keep every indicator for all these variables except intention to donate and intention to volunteer. Okay? That's why we have 64. So your dimension is 64. For K is the number of participants. We have for 509. Okay. So the next part is identifying T. For T, what is our optimal iteration? So we have to simulate it again. So I'm going to open this file. Let's move to the next one. You have to test your parameters. If you have 12 parameters, you have to test all of them. So you have to test parameter from parameter 1 up until parameter 12. Okay. Say parameter 4 up until, okay. Don't forget to test all parameters until parameter number 12. Okay. Okay. So for example, we'll test just one parameter. I'll just copy our value 10.4 and 1. Let's just copy this one 10.4, 1, and 1. Okay. And we have also indicated that part in this one 10.41 and 1. Okay. So the next part is to, this should be cleared. For this one, it's up to you. How many kinds of iterations do you want to test? You don't need to research some studies for this. It's just really up to you because your error would be very much dependent on your model. So let's say we wanted to test 5, 10, 15, 20, 25, 100, 200, 300, but I would not recommend more than 300 because it takes a lot of time to run the model. So maybe just about 150, maybe 150 will already do, would be already fine. Okay. And don't forget to test at least 10 t values. Okay. So this should be the standard for elbow method, finding our optimal t or optimal iteration. You should always test 10 t values. So for example, this 5, I'm going to test this one. You have to put 5 in the model in this part. Okay. This one. You have to put 5. Okay. And then you have to move your cursor up until the last slide. So in the last slide, you have to remove this percentage sign because for this part, this will show your elbow method. I'll include this. This is for your elbow method for finding optimal T. And then you just have to run. Let's click run. Mhm. Okay, just a minute. It's still loading. Okay. So in this part, mm, okay, you'll have this figure. And in this figure, you have to find the elbow. Again, when we're looking into the elbow, we have to find what is the corner point. But if you take a look at it, in this corner point, this one, it still kept going down. So if the figure, if the line in the figure rather still keeps going down, then that means you don't have a stable GBS fitness at this point. Because you have to keep to find, let's say, to find the corner point with a straight line. So if your figure is like this, you have to run it again. Let's run it again.
And
Okay, this
everything is
one.
the same. Everything is the
Hmm.
same. The parameter is the same. You didn't change anything when
Oh,
you
no,
rerun
no.
that.
Oh, no. Yes, you just have to run again. No needs to
Ah, I
change
see.
anything. Yes,
Okay.
yes. All right. So this is what we're looking for. So we really wanted to find what looks like an elbow because we wanted to find that stable value. So for iteration of 5, we can see that our optimal T is 2, and this is our G best fitness, 17,371.7. So you should always save every figure that you have for elbow method. Copy figure, this one, and then edit, and then copy figure. Okay, and then you can paste it here. The reason why we wanted to save everything in this part because at first I was afraid I did not really include this one in my research paper, and then fortunately the one of the or none of the reviewers
Reviewers,
rather
yeah.
asked.
One of the
Yeah,
yeah.
not
The reviewers
none
asked
of
that,
the
yeah.
reviewers. Yes, yes. So you really have um to document everything so
Save the
that you
file.
won't start everything from scratch. Okay. So in this part, you just have to copy this one. So your optimal T is 2. You put 2 here. And your GBest fitness is 17371.7. You can also copy it in this part. Okay, this one. Okay, this is your GBest fitness. And then copy it in this part.
So Maela, we just find like one the lowest, in all of those parameters, and we just find like the lowest optimal
Mm-hmm.
T or the optimal
Yes.
G best. Which one?
Oh, for the GBest fitness, the lowest
Okay.
GBest fitness.
We just figure it
Okay.
out, right? From all of
Mm,
these 12, and then like inside of that, we just try and error also.
right, right. That's correct. Okay.
Wow.
So,
Okay.
so it's a constant simulation, Doc Yogi. That's why it really takes a lot of
But
time.
for the T is like for example, the setting in parameter 1 and parameter 2,
Mhm.
the T that you test like 5, 10, 15, 20 should be the same in parameter 2
Mm.
and
Oh,
parameter 3.
yes, yes. It should always be the same. If I tested this one, it should also be the same
Oh,
for
the same,
this
right? That
part.
one, right? Yeah, the
Mm.
same. We just
Yes,
changed
yes.
the parameter, the
To this
NW.
one.
Yeah, 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 yeah. Okay,
Yes,
okay.
yes.
Okay.
Okay. All right.
Three of you boys understand? This is like totally new field for you. Okay, next.
Mm-hmm. Okay. So I'll just copy this so that we won't forget. Okay. So next part, let's say I'll just test again. So just for benchmark of comparison. So next is T of 10. So we just have to move to the first part of the code and then again change our T from 5 to 10. And then let's run our model. Okay. Okay, this one. This is your figure, and again, it still keeps going down. So we need to have the straight line in the elbow part. That's why we have to run again. So let's run. Okay, so this is what we're looking for. That means you have to click this one. Again, don't forget to click this one. Optimal T is 9, edit, and then copy figure. Then copy this one, T equals 10. And then copy your optimal T, that's 9. And then let's copy it from this part. Okay. So next, let's just say I'm going to test parameter 2 just for comparison as well. So for example, for parameter 2, 20.4 and 1, 1. Okay, so 20.4, 1, 1. So if you're going to test a new parameter, please do not forget to change your parameter here. So what we changed over here is the number of particles or number of n. We have to change it from 10 to 20. And the rest is still similar because we have 20.4, 1, and 1. Okay. So let's go back to t is equivalent to 5. And then let's run our model. Okay, so the result is still not acceptable because again, it still keeps going down. We have to run it again.
How many days for you to finish all of those?
Oh, it really took a lot of time, Doc Yogi.
I mean,
Too
yeah, I
many.
know. I mean, I also did PSO before, and one of my publications did PSO. I think it took me like 2 weeks only for getting the table, the
Oh,
complete
maybe
table.
I
Maybe
took one
more.
month.
Maybe yeah,
Yes,
one
more
month
than.
perhaps. Yeah.
Oh, I think the entire thesis one. I just spent it
Only
for
for
my
spending
entire
on
simulation. Yeah, so
only for the
3 months.
simulation. Wow.
Yes.
Wow, 3 months only for
But
getting
oh
that one
yes.
complete, right? Yeah, okay, okay.
Mm. But it also includes my lecture with Doc Sarah because I'm not yet familiar with PSO. So I'm
Oh,
still
okay, okay.
checking if it's correct or not. hmm Okay, so again, we have to run again because it's still not a good model. Okay, so this one. All right. So this is a good model. Our optimal T is 3. Edit, copy figure. And then let's save this for documentation purposes. Your optimal T is 3 and your G best fitness is this one. Okay. So let's just say that you have already run all your parameters from parameter 1 up until parameter 12. Okay. You should test everything and again test at least 10 t values. So let's say everything is filled in already. The one thing that you should look at is the one with the least G-best fitness. So find the least G-best fitness.
Can you give me one example that you in your publication that already finished using this one?
Mhm.
Like you have the complete one, the previous one. You still keep it?
Oh, it's not in my laptop right now. Okay. And then, okay. So right now, we're going to find the least value. So the least value is this part from 17372 17014 17255. You can also utilize mean for this part and then mean. Okay, so your minimum value is this one. Mm, okay. So that means this is your optimal T. Again, this is just your optimal T because this is the minimum value among all the tested values. So you have to remember this one, 10 and 9, because you have to transfer this part into the next part, this one. So you have to transfer your 10 and your 9 T in this part, again, 10 and 9, and you have to copy your parameters. So again, these are your parameters, 10.4, 1, and 1. Okay, this one. So the next step is run again the model. Run the model using these methods. Or sorry, using these parameters. So you have to run it again, 10.411, using t is equals to 10. Why t is equals to 10? Because we have to check this first combination first. Okay, so let's run this. But in this part, you don't need to save your elbow method already. So you can just close your figure. You can close the figure by putting percentage mark. Okay? If you put percentage mark, it won't show any figures. Because what you need is the GBest fitness. The GBest fitness is located here. So you have to copy this one. Copy this one and place in this one. Next, run it again. Run it again without changing your parameters because you just have to find your overall mean using 10 runs. And then again, copy your GBest fitness. Copy it again. So run it again. Then
This
copy.
one, guys, this is
Mhm,
actually for testing the consistency, because like
mhm,
we don't know, sometimes like we are just lucky, in that Omar, Jimmy, sometimes we are so lucky, like we find like one dot,
mhm.
like we don't know,
Right.
like perhaps like that's actually a good one or not. But now we would like to test, the consistency. That why we would like to check the mean, standard deviation, mean, and max. Okay, that's
Mhm,
the
right,
logic.
right.
You
Mhm.
got it, three of you? Yeah, okay, good. Next. Oh, yeah, let's
Okay.
imagine we already finished that. Yeah.
Okay.
Okay,
Yes,
okay.
yes. So let's say that we have already run them 10 times. And again, by the way, you always have to run them 10 times. It's actually a standard, as always, in any kinds of machine algorithms. You always have to run everything by at least 10 times. Okay, so let's say we have already finished all the 10 runs. Next, we have to change our t from 10 to 9. So again, change this part from 10 to 9. Okay, and then 10 to 9, let's run it again because you have to copy your GBest fitness. Copy this one and then paste, then run it again. Okay, and then copy this one again and then paste and then run it again. Okay, so you have to keep running your model for 10 times using the same parameter. Okay, I'll copy this one. I'll copy the GBest fitness and then paste it. Okay, so now let's say we have already run these two combinations for 10 times. What we wanted to find is the one with the least mean. So the one with the least mean is this part because 17103 is less than 17251. If you already have the least mean, that means this is your optimal T. That means you have to use 9 as the number of iterations. Okay?
For the final one.
So 9. Yes.
Yes.
So this is the final iteration. So a while ago, we subtly talked about how many iterations should we prepare for the particles. So we have only tested 5, 10, 15, but right now we already found that the best optimal method, it's let's say, is 9. Okay, so you have to put 9 over here. And then the next part is to find the values without the combination of k-means and PSO first. So this will allow you to gauge whether you really need to perform PSO because it might be a surprise if you don't need to do so. Then it would be better if you won't need to do so. But of course, I think
In
it's
general, no, impossible.
yes.
In general, yeah. In general, impossible.
Yeah.
It's like this one, for example, Omar, you want to find like which one is better, A or B, like a B is actually with extra oil. That oil is actually PSO. But usually, you know what? Usually in general, with the extra PSO, yeah, it's much better,
Mm.
more delicious.
Yes, yes. So we don't really want a shortcut method.
It's
So we
okay.
want
Yeah, this is the
everything to be
logic. Yeah, this is the
organized.
logic. Yeah.
Yes. Okay. So, oh, by the way, I just remember because in my initial study, I did not utilize this part, this K-means part. That's why in one of the panels, Dr. Satria, sorry, Dr. Vera, if I remember it correctly,
Dr.
asked
Vira.
me,
Dr. Vira
yes,
attack you about that.
Dr.
Yeah.
Vera.
Thank you
asked
about
me
that.
what's my basis.
Yes,
So
what's your
that's why
basis?
I
Yeah.
really had to include this. Unfortunately, one of the reviewers also asked, what's the purpose of integrating both? So it also gives us the feeling that we really have to show these K-means part. Okay? So for the K-means, you have to check this one. Another code. K-means only code without the PSO part because I removed the PSO in this part. So again, we have to copy the same parameters, 2310.411, 2310.411, and then 64, 509, and 9. So you just really have to copy your parameters, and then you just have to run it. Okay, so this is already your SSE. Again, in K-means, you only have SSE, not GBest Fitness, because GBest Fitness is only for an algorithm with PSO, while SSE is for K-means. But then again, they do have some similarities. All of them talk about the error of the model. So you have to copy this one, and then you have to copy your SSE and paste it into this part. Oh, sorry, I actually forgot to include this one, 10, 20, and 30. Why did I utilize 10, 20, and 30? Because in K-means, you only have N. You don't have this one. You don't have W, C1, and C2. And your N are 10, 20, and 30. That's why you're only left with 10, 20, and 30. So it's only a varying of 10, 20, and 30. And then our M is this one, 23. Dimension is 64. Run is 10. And our optimal T is 9. Okay, so we were able to remove them. But as you can see, we still have these values over here. So you can just remove them. It's totally fine. Or you can just input percentage.
Small r. What is that one? I forget.
Oh,
The in the table.
small r is number of runs
Oh,
for
number
this
of
one.
runs. Okay, 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 okay.
Okay, all right. Mhm. Okay, so again, you just have to run them 10 times. So run it again and then copy your SSE, then paste it. So let's just also say that we have already run everything 10 times. We have to move from parameter 1 to parameter 2. So you have to change your n from 10 to 20. From 10 to 20, you have to change this part and then run it. So this is your value. Your SSE should be placed here and then run it again and then copy and then paste. So next, let's say we're going to test 30, 30. Then let's run it again, copy, mhm, and then paste. And then you have to run it again, copy, and then paste. So for hypothetical scenario, let's say we have run them 10 times and we already have their respective means, standard deviation, minimum, and maximum values. We only have to focus on parameter with the least mean. So everything should be the least value. And in this part, the least value is parameter 2. This
Hi,
one.
Professor. Sorry to interrupt.
Mhm.
Can I please see the MATLAB again?
Okay, sure. This one.
You ran this. I thought there was no C1 and C2.
Oh, yes, you can actually remove them. Okay. So let's say I'm going to remove them. We're left with,
Also,
mhm.
oh,
Oh,
okay, okay.
sorry. I forgot this one. So you can remove them and then you can also run them. you're still presented with the same result. I just forgot to
Oh,
remove them.
oh,
Okay.
okay, okay, okay. Thank you,
No
thank you.
worries. Okay. Okay. So let's just remove them. Okay. Any other questions?
No, for me. Yeah.
Okay. All right. So again, our optimal parameter for this part in the k-means part is parameter 2. Okay. So that means your optimal n is 20. So later on, what's the purpose of finding the optimal parameter in k-means? Because you have to check if your mean, if your SSE mean in this part is lower or higher than the k-means and PSO part. Okay. So right now we're going to integrate both k-means and PSO. We're going to go back again to this MATLAB code. So you have to run your model again using your parameters in this one. Okay, sorry, in this one. So you just have to copy them. So for example, you have 10, 20, 30, point 4, point 7, 1 and 2, 1 and 2. And your t is 9. So you have to input your parameters one by one here. So you can just utilize this one, copy, and then transpose. Okay. All right. And then your t is 9. Okay. And let's just say I'm going to copy this one as well. It's 20.411 and this should be like this. And then 9. Mhm. I'll just make them organized. Okay. All right. So you have to test from parameter 1 to parameter 12 again. So let's say we're going to test k-means and PSO using this parameter 10.411 and 9. So this one 10.411 and then 9. But in this part, you have to ensure that these should be in percentage because we don't want our figures to show at this point because we don't know our optimal solution just yet. Okay? So you just have to focus on this part in the initialization part. Again, you have to run it. So this is what you wanted to copy because this is your G-best fitness or the errors model for k-means and PSO. And then you have to copy it. So similar to the previous one, you also have to run them 10 times. So after running them 10 times, you have to find what's your mean. Okay. All right. So let's move on to the parameter 2. I'll change this to 20, 20.411 and 9. Let's run it. This one. Okay. And then let's run it again. Okay. And then copy and then paste this one. So until everything is already simulated in the model. So you have to run everything 10 times. You also have to copy and change your parameter 12 times because you have 12 parameters at this point. Why does it have a value? Okay. And similar to our previous method, you wanted to find the least mean. So between them, so for example, again, we have run them 10 times. The least mean is this one. This one. Parameter 2. So almost similar to the ones we have presented in this k-means because the n is 20, but it's not always similar. So this might only be a coincidence just at this point because we have just run a few parameters. So as you may have noticed, we have 21,437.05 mean. So that's about 21,000 error. But in this K-means and PSO, you can already see the huge difference. So coming from 21,000 down to 16,000 error rather. So it definitely shows that you were able to reduce your error for about 5,000. Okay. So you can definitely show to your research paper that it's really helpful to integrate PSO into the K-means method and not just utilize K-means as it is. Okay. And then let's say you already run everything. You have to find your lowest mean because that is your best G-best fitness. Because again, why it should be the least because we're pertaining to the error. And the worst G-best fitness value is the one with the highest mean. And you can also show the one with the lowest standard deviation because that means how clustered and how compact your SSE values or your GBest fitness values are. And when we say highest standard deviation, you can actually show some similarities with highest standard deviation and highest mean. It's always somehow similar because if you have the highest mean, then that means you might also have varied GBest fitness values. Okay. Oh, I think Tokyogi for this part, I still have my data. Should I show it?
Just the final table, just the final one, perhaps. Just example,
Yes.
yeah. One example, the
Yes.
final one.
Yes, just the final. But the initial I don't have in this part. Mm, mhm. Okay. All right. Okay. So I still have the one with gamings. So this is from one of my studies. So just to show, I have included, okay, this one. This one, we have tested three parameters as well because in this study, I also utilized 12 parameters with these corresponding n 20, 30, and 40. And as you may have noticed, my least SSE value rather is this one, parameter 2. Parameter 2 with n of 30. It's 7,049.09. But if we're going to take a look at the combination of PSO and K-means, so this part. Okay, so again, you have to run them from parameter 1 until parameter 12, and then you have to find the minimum value. So this is my minimum value, 6415.86, and that came from parameter 12. This one. Okay. So that means this is your best parameter that you can showcase to the model. So this means that this is superior more than anything else in the parameter that you have tested. So you can also take a look at it that the 10 parameters we tested are almost similar to each other based on this figure, except for our outliers. So in your study, you can recommend not to assess these two outliers because they actually produce an entire different GBest fitness. So it's really good to hear that we were able to test at least 10 parameters. So not just 10, but you have to exceed them. At times, you really have to perform more than 10 parameters just to really ensure that you were able to cover everything. Okay. And then, okay. Mm-hmm. All right. So, up until this part, do you guys have any questions? So, that's it for how you can run the PSO K-means part. What I'm left with is the plotting, which is
Supervise.
easiest.
The plotting, the last one, the plotting. But after
Mm-hmm.
that, they have to learn the supervise. This is just the
Mm.
unsupervised.
Okay. Oh, no worries. Supervise is easy. We can combine it with SEM.
Yeah, that's why. Like
Mm,
this is still unsupervised first. Then after that, we will go to supervised. Okay.
mm. Okay. All right. So the last part is just the plot for us to really complete the K-means and PSO because without the plot, it won't be considered as K-means and PSO because this best visualize our model. So you have to remove our percentage. Again, if we remove these single percentage, that means we wanted to show the codes that we have inputted here. So we have to run it. And by the way, don't forget if your, let's say, if your parameter, I'm going to pause it. Let's say, let's go back to our optimal parameter. Let's say your optimal parameter rather, is this one, the one with least mean. This is what you're going to run. Let's run it. So 20.4119. Oh, it's similar. So sometimes it will give you an error like this. You just have to erase this one and then run it again. And at this point, you might ask, let's say, for your first run, will it produce a similar result compared to the succeeding runs? It must produce the similar result. It's just that you'll have a different group. So, for example, I'll copy this one, I'll copy this figure. Mhm. And then run it again. So regardless of the number of runs, you should always find the similar solution, but your figure will vary. And then I'll copy it again. Okay. If we're going to take a look at it, you can find some similarities. Mhm. Okay. Right now, I don't see any similarities because if you're going to skim through the figures, there are no similarities. For example, for this cluster, for cluster 14, it's not, is it not? Okay. So they are not really evident in each figure. So that only means that this is not your optimal solution. If they do not have the same figure or the same set of clustered groups, that means they are not your optimal solution just yet. So I'm going to show you an optimal solution. It should be, mhm. Oh, I did not include it in this part. Let me just check it again.
We've published this paper already.
Ah, yes. Okay. All right. So this is an example. Mhm. Okay. So if you're going to skim at it, this one, the cluster one is similar to for every types of plots. The cluster one is still in the same in the same position rather. So that means this is your participant. By the way, for every cluster, you have participants because again, in K-means and PSO clustering, we have to group the similarities among all our participants. So that means they do have some similarities with all the features, sorry, with all the indicators that we have included. So among all those 64 indicators that we have included. And if you're going to take a look at this part, for example, in cluster 10, you can also take a look at it later on. I'm going to show what it's like in number basis. So in cluster 10, this part, it can be seen in this where else is it? Okay. For cluster 10 in this part, you can see it cluster 6 in this part. Okay. And you can also see it in this part for cluster 8. And then you can also see it for this part in cluster. Mhm. Let me check it. Okay, oh, this one, 15, 16, 17 in cluster 17. So again, in this scenario, that means if your groups or if your participants in the clusters are just the same, regardless of the number of runs, that means you already have your optimal solution. Not like this one wherein you cannot really see the
Totally
similarities
different.
among, yes, among the figures. All right. So you really have to check everything. But I know it's too difficult to check over here, so you can utilize this part. Okay. So you have to click this one, IDX. When we say IDX, we're pertaining to the cluster numbers for each participant. So for example, your participant number 1 is in cluster 8. So in our figure, it's going to be like this. This is your cluster 8. So your participant number 1 is over here. That's why it's colored over here. And you can definitely see a lot of cluster 8 here. So you can transfer this one into an Excel file so that you can compare them easily. And then you should have 509 participants. Let's check. Okay. So from they are clustered from 1 to 17 because your optimal cluster is 17. Okay? All right. So now let's say that you already have your optimal solution. Let's cross this part. Let's say you already have your optimal solution. So just for an example, this is your optimal solution, even if it's not. Let's find its another cluster method. So in another cluster method, you have to, I'll change this one into this one, the one without headings. Is it XLX? Okay. And then you have to create another Excel file, which is this one. You have to create this Excel file. I'll just include it as IDX. So you have to transfer your IDX to your Excel file so that you can call it out over here. Okay, so type the file name IDX and it should be saved in one folder only. And for this part, you have to change this one. A while ago, we mentioned that we have found 17 optimal clusters. So the numbering would start from here. This is your cluster 1. Mhm. This is your cluster 1, this is your cluster 2, and onwards. So this does not hold any means at all, but we have to set it as a standard. So you have to find up until cluster 17. This one. This is your keyword for this one, cluster 17. Mm, 17. So you can remove everything already. And let's say you still have plenty of clusters, you can just add another one. You can just say 18. So this is what you're going to add, 18. And then don't forget to change your sign. When we say this one, it actually talks about, when we say G, it talks about green. So these are the colors. So you can visit MathWorks. MathWorks, okay, plot color. This one, for this link, you can choose any kinds of color you want. So you can choose R for red, G for green, B for blue, anything that you'd like. You can definitely customize them. For this one, it pertains to the mark points. So meaning, is it tagged as green with X point or green with circle point? In this part, you can check this one to the line plot, this link, and then go to the last part. Oh, they're in similar. Oh no, they're in a different form. So this one, circle for O, plus sign for plus, asterisk, point. So anything that you really wanted to show in your cluster figure. Okay. Oh, and don't forget, by the way, to change this one as well, because this pertains to your cluster if you're going to add another cluster. And then do not forget to remove our percentage sign because we wanted to show our cluster values. We have to show them. Did I change everything? Okay. And then for this part, you can just say up until cluster 17. So you can just remove everything. And then you have to copy it from cluster 1, cluster 2, cluster 3, cluster 4, cluster 5, and so on. You have to copy them up until cluster 17. So let's run this first. So again, you have to put legend. I'll put it here. Put legend up until cluster 17. So
Let this
let's
one
run
be the
this
last
part.
one, Maela. I think let this
Mm-hmm.
one be the last one. We can save it for
Okay.
next week. Yeah.
Okay, okay, sure. 64. Mm, okay. So this is the plot that you wanted to showcase to your journal because this shows how compact and how clustered your groups are. So you can definitely see. So if you're going to put all clusters here, it should be from cluster 1 to cluster 17, and all the legends are located over here. So you can also maximize this one. Okay, so like this one. Okay, and don't forget to always interpret it how compact they are using lots of, even MS Excel tool will definitely do lots of figure and data analytics tool or even Power BI to interpret the clusters if you just also wanted to interpret them in that way.